All right, hello everyone, good evening. My name is Sam Saccone. Tonight I want to talk to you about the future features for the web and a look into some new performance patterns that these new primitives unlock. A little about me, I'm an engineer at Google. I spend my day wrangling some Python, and if I'm lucky, writing some JavaScript, and then if I'm really lucky, figuring out why a web page is slow. So let's get into it. I think that we're at this awesome inflection point where we have so many new primitives that are coming at us every day, every week it seems, that unlock these new potentials, these new ways that we can make our web pages even faster. But if you're like me, you might feel a little overwhelmed. It's hard to keep track of all the new features that are landing in the browser every single day, and as Eric Beitelman put so well, this was a couple months ago, but he said over 1,000 features in Chrome have landed, and that only took 4 years and 7 months. So I find that a little hard to keep track of. So which of these features actually impact you, and which ones will help you make your web pages faster? Well, that's a little bit of what we're going to get into today. But before we can talk about performance on the web, it's really important that we establish a common language of how to think about performance and how web pages load and exactly what makes them fast and what makes them not. You can think of performance as having 3 primary phases. The website initially goes through a network-bound phase. This is a fancy way to say that files download from your server. Okay. Once we have our assets on the page, we go into this parse and execution-bound phase. And this is when the browser grabs the assets that it downloads, it reads the string files or binary data, and determines what to do with that data, whether that's turning the JavaScript into something that the VM can execute or taking an image and rastering it to the screen so you can see it. And then finally, when we have all this data and the browser knows how to read it and understand it, we go into a render-bound operation, where the browser says, okay, this paint's here, this JavaScript executes and manipulates this element and makes it animate. As Lynn said, our menus open and close and animate, hopefully at 60 frames a second. Now, the first part of this is bundling. Bundling is a kind of old concept, and if you ever Google how to make your web page fast or read the first chapter of any performance book, it will say the first thing you need to do is minimize your image and compress your assets and put them together. So your web page might look something like this. If you've ever used something like Rollup or Webpack or Gulp or Grunt, you have a file that's appbundle.js, vendor-bundle.js, and styles.css. Your app bundle is going to be all of your code, your main.js, your plugin.js, etc. Your vendor bundle is where things like Backbone and React are going to get put into, and then finally your styles file. The thought being that your vendor assets are going to change less, and your userland code or main.js is going to be changing a lot. So when you change your business rules, the only file here that will have to re-download after that is your app bundle. So you're getting some savings. Now, as I said, bundling has been the gold standard of web performance. Most books will tell you you need to do this. Most articles, most blog posts will say you need to bundle things to make your website fast because every single request is going to require a new network connection and it's going to be slow otherwise. Now, with the advances in networking in HTTP 2, which allows for parallel downloads to happen on the same connection, these rules are no longer quite true in every case. And actually, there are some non-trivial performance downsides to using this bundling approach where you stick all your assets in 1 or 2 files. So let's imagine my simple website here where we have our app bundle, vendor bundle, and styles. Now, if you'll notice, we have a file that's in common between our app bundle and our vendor bundle. And think of this like a file that needs to be in both of the bundles for them to be valid bundles. So if you loaded one without common.js, it would error out because it was saying, oh, I needed this variable that was defined in common.js and it wasn't here. And the same with appbundle.js. So you have this overlap in your sources. Now, when you change a single file, all the dependent bundles are invalidated. What does this mean? Well, if you go into common.js and you change your constant time from yesterday to today, now all of a sudden, on the repeat load of your page, you have to re-download app bundle and vendor bundle. So this invalidates both of these bundles. And reloading this page and having to download these again comes with some not great performance downsides. So imagine if we took our website and we broke it up to be individual JavaScript files and individual CSS files, where we shipped 4 different JavaScript files and 4 different CSS files. Now what happens when we invalidate page2.js? Well, all the other assets are already cached in the browser. So the only file that has to be re-downloaded and reparsed and re-executed is page2.js, resulting in a super fast second load. When we ship these granular assets, there are some other wins that come along with this approach. Now let's step through the normal loading phase of a single JavaScript file. The file has to be downloaded from the network. The file then has to be turned into a string of JavaScript into something that the engine, the JavaScript engine, can understand. So that's called the parse phase, where it turns it into a typically binary representation of the data or an abstract syntax tree. Then from that, the JavaScript engine has to compile it. And this is where it goes in and does some inner working magic to actually make it fast. And then finally, that code has to run. And this takes, depending on the size of your script, a non-trivial amount of time. Now, when we start shipping granular assets, we get this cache load, which means that the browser has the asset in its cache, so it doesn't have to re-download it. But we still have to pay this parse, compile, and execute cost. But we have some significant savings just by splitting our assets up. But wouldn't it be great if we could speed up this parse and compile phase as well? Well, it turns out that we can, and browsers are pretty smart. Chrome, for instance, will notice if you load the same JavaScript file 2 to 3 times, and it's exactly the same, it'll say, oh wait, I already know about this. I've already parsed and compiled this multiple times. So I'm going to reuse this parse and compile and apply it on top of your file. And what this results in is about a 40% reduction in parse and compile time. Again, it might not seem like a huge number, but when you have many scripts and you're loading a page over and over again, this actually adds up to a non-trivial time saving when you're visiting a web page. This is a number that's changing, but it's something that the V8 team, the JavaScript engine inside of Chrome, is actively working on driving down, so to make it more and more cache hit per file load. So as you can see, by shipping granular assets in this case, we have significantly improved the time to execution on our single JavaScript file. Now, the second part of this granular asset story is having the ability to download individual JavaScript resources within our page. For a long time, you had to have a loader, something like AMD or jQuery, to go in and download scripts for you, and you had to programmatically do this and wait till they were done to do anything. But today, with script type module that is shipped in, I think Firefox has it now, and Chrome has it, and a couple other browsers have it. On Nightly. I knew it landed somewhere. It's on Nightly in Firefox. So with a script type module, we have the ability to load unbundled code via ES 2015 imports. So this means that you can have each file script type module, and you can type import directly in that script tag, which is super cool. Some Chrome engineers, after they landed this, thought, well, OK, now that we have this, can we load common JavaScript files totally unbundled? And they did this with Moment.js. So Moment.js has many files, and so they tried to do an example where they loaded it in an unbundled state using script type module and imports, and in a bundled state where they took all the files and concatenated them together. And what they saw was that there was a significant performance gap loading things unbundled. So even though you can, doesn't always mean that you should. So going back to this concept of shipping granular assets, even though we can, the good performance characteristics are not always possible and they aren't exactly possible today. Well, yet. So why are we talking about granular loading on the web then? It's a good question. In the near future, you can think of your clients as not needing a one-size-fits-all solution. So if you're on a connection on your phone with a bad 3G connection, and if you're on a fiber line that goes direct into your house on a desktop computer, you can get different experiences and different loading experiences. So by having an understanding of your client's first byte, you can ship a different experience, and you can do this all within the browser. So to make this possible, and to unlock this ability to ship granular assets for one person and a bundle for another, we need to be able to understand the client conditions and make determinations at runtime about what we're going to load and how we're going to load it. Dynamic imports are something that's in Chrome today, and you can do code like this without a compilation phase. You can say if should fetch now, await import awesome.js, else nothing to see here. So this might look simple initially, but think about it for a second. In our runtime, we are dynamically importing a JavaScript file and importing a module export and then running it. Using promise syntax with await, we can do this all in the browser today. No build phase. And this is, again, in a conditional point. So this could be conditionally done at any point. It doesn't need to be statically analyzable. So now we have the ability to do dynamic imports. Well, the next part of the puzzle is looking at our client's network information. In Chrome, this API has shipped today. This gives you all kinds of really cool things about your client's network information. You can look what type of connection they have, their downlink, their round-trip transit time, which is the time in between sending a byte and getting it back, their download or downlink max, and their effective type. So when we take dynamic imports plus script type module plus network condition, we can actually load our experience for our user in a different way depending on their connection. So in this code example, we're saying if your round-trip transit time is over 500 milliseconds, we don't want to pay the hit to download every single script file independently. We're going to download a bundle and get the user on their way as fast as possible. Otherwise, we're going to download page 1, page 2, mobile.js, wait for those all to resolve, and then execute our page, which enables you to get those wins of shipping granular assets along with the wins of shipping the ideal experience for your user, depending on their connection. So with client conditions plus dynamic imports, we can start delivering optimal performance across the multitude of client conditions, which is really exciting for me because we no longer need this one-size-fits-all solution for every single person that visits our web page. Now that we have our bundle, I want to talk about getting to the state of the page being interactable, meaning the page is loaded, but maybe you're executing a bunch of JavaScript and it's locking up the page and your user can't click on things. Let's get the user to something that they can click on and interact with faster. I think like our loading story, we're at another one of these inflection points. We're moving from a client fetch model to a server push model, from a lazy to proactive asset discovery model, and finally from an inferred priority to an explicit priority model when it comes to network resources. The first one I want to look at is cache digest for HTTP2 push. And this boils down to adding the ability to control what gets pushed to your user. So you may have heard of HTTP2 push, or you may have not. I'll give you a quick 1-minute explainer. Basically, when a user visits a page, the page doesn't have to discover assets and ask the server for those assets. The server can start pushing those assets directly to the client before they ask for it, meaning that the bytes have arrived before the client even asks for anything, which can result in a significant speed up on your page. So let's consider this following situation. Let's imagine your client has assets A through D cached locally, and the server is pushing assets at the same time. It says, hello, you're visiting index.html. I know that you're going to need assets A through F for the page to be interactive. But in this case, since the client already has assets A through D locally, pushing A through D from the server is redundant, and it actually causes network contention, which can slow down the page load time. So I call these assets overpushed. With cache digest, it adds the ability to tell the server what assets are in the local client cache. Now, there are a couple cool solutions for this today that you can put into your server if you wanted to, but this is clearly a problem and is something that the platform is working on solving for users. So, with this concept of client cache, asset discovery, the page would load, or start to load. The client would say, hey, I have assets A through D. The server would say, OK, I see that you have A through D. I'm not going to push those to you, and I'm only going to push E and F. So this solves the problem of overpushing, because the server only is pushing exactly what you need and nothing more. But this might seem like a silver bullet, something magical. But HTTP 2 server push can get you into some pretty big trouble. When it comes to delivering assets, main.js is probably more important than ads.js to your user's experience, or it might be flipped depending on the experience you want to ship. So, wouldn't it be nice if we could hint to the browser what's important and what's not? What happens is that priority hints are a proposal to do exactly this: explicit priorities versus inferred priorities for any asset on your page. You can think of the browser as a gigantic inference engine. Usually, it does a pretty good job. It says, OK, I see this image is high on the page, so I'm going to load it first, and I'm going to defer loading these images below. But sometimes we want more control as developers because we know better than the browser knows. Now, there used to be some, or there are some tricks to hack around this. Loading a JavaScript file in an image tag to get that loading first. Things like this, to force things as low priority and high priority, basically working around this JavaScript inference engine. Not great. And the goal with this priority hints API is to remove priority hacks to unlock explicit priorities versus these hacks and implicit priorities. So this is a little, like this was a mock of what the API might look like. It's still in a pretty early phase. But if you notice, we have these groups. Now, the groups tell the browser what it should be loading first and what it can defer. So it says on my favorite hat site, I'm going to say my favorite hat is the most important. You can wait on the coolhats.gif, and you can wait on the hat store. So it will download and prioritize favorite hats first, and everything else will get pushed out until the main thread is open, and it has some time to do some more work. Now, this extends more than just markup and HTML tags. You could also do this via the fetch and the controller that you could pass to the fetch call. This is in JavaScript, so you could say this fetch is low priority. I'm going to defer this. And there are some other really interesting proposals in here to do things like batching of fetch requests. So if you have a bunch of late priority fetches, it will take all of those up, bundle them, and ship them off to the server. But I recommend you check out this link. It's some pretty interesting ideas. But overall, this unlocks this ability for you as a developer to tell the server and to tell the browser what's more important and what's less important. Now, we were looking at images, so I'm going to tell you a little story about images in browsers and a way that they behave that's a little surprising. Async images is an intent-to-ship API in Chrome, and I think in other browsers people have bought into it. It unlocks this explicit control over image decoding and removes it from the critical path. So you might say, well, images aren't in the critical path. I don't think. Well, it turns out that for very large images, they are in the critical path. Let's imagine this page, very simple page. And I'm loading a very large image, maybe 100 megabytes. See, when that file downloads and it finishes downloading, the browser has to read all those bytes and figure out how to paint it to the screen, which takes significant resources. So much so that it can actually cause contention with app.js. So the page will be loading, and then app.js will get stalled because the browser's busy painting this image. So I've illustrated this to explain exactly how it manifests. So imagine we have our image downloading, our script downloading, our image decode, and then our script parse, compile, and eval phase. Well, this time right here, the script parse, compile, and eval was blocked by the main thread because the image was busy decoding in the browser. With the async decode proposal, this tells the browser, go ahead and don't block the main thread when this image downloads. Wait till the main thread is open, and then you can decode the image and paint it to the screen. So with this, with an async image, the script parse, compile, and eval is no longer blocked, and the image decoding happens afterwards, making the page more responsive and faster to load for your users. All right, so we've talked about bundling, loading. Now I want to get into my favorite part of web performance, runtime performance. This is the actual interaction of your page and your user as they're progressing through your application. So I want to talk about how to move work out of the critical path and how to do more work without impacting user experience. Onto one of my favorite APIs, the Web Worker API. Now this has been shipped for a long time. This has been in the browser. It's just been sitting there asking for you to use it. All right, not many people are using it, but I'm going to convince you. So let's imagine your browser. This is in the center. We give it tasks, it does some work, it hands the tasks over. But if you're like me, I want the browser to do lots of things. I want it to do lots of JavaScript, execute lots of React, update, tree, diff. No. OK, so the browser gets busy, it gets overloaded, it feels the contention, things slow down, it gets janky. But with web workers, the browser can spawn little helpers. It takes a task, it hands the task to one of its worker friends. When the workers are done, it hands the task back. And the browser can do more work without causing user jank or performance pain points. So to illustrate this in a little bit more of a real-world situation, well, it's not real-world, unless you have to move boxes across the screen. Then it's really perfect for you. But on the first one, I'm moving a box, imagine that, across the screen. And on the bottom, I'm moving that same box in a web worker across the screen. And I'm passing the box pixels to the main thread so it paints, but the main thread actually isn't doing anything to calculate the box position. As we can see, the worker thread is moving a little bit faster than our main thread. The main thread's having a hard time, a little stuttering along. But the worker thread, because the worker doesn't have to be concerned with how to paint the page, how to react to user input, it's only concerned with moving that box, it can do that a lot faster. And the main thread's only concerned with taking the data from the worker and painting it to the screen. So you get a better user experience. Now you can take this and more generally apply it to things like your normal web page and updating a form and calculating data, which can be very useful, especially to your users. But one of the first things you'll discover upon working with web workers is there's no access to the DOM. And as a web developer, using the DOM is kind of important because it's how I interact with my user. Well, luckily, there are several proposals and several polyfills to do exactly this today. One of them that I like, that some of the Chrome people have been interested in and are sort of forking into another proposal called Async DOM, is DOM change list. And this is a proposal to enable the construction of DOM operations, and this comes out of the Ember team. What this does is you can create a new DOM change list, create a bunch of DOM manipulations, pass them into a worker. The worker can then determine what it wants to do, pass those operations out, and apply it directly to the DOM. So we have DOM access. We can do a lot more work, but I want to share data with my worker because I have to pass data in and pass data out. On average, post message, which is how you do this, has about 10 milliseconds of overhead every single call, which doesn't really matter if you're only making a couple calls, but if you're being very chatty and sending a lot of messages back and forth, this can cause some issues. So on to everyone's favorite topic. Again, as Lynn pointed out, shared array buffers have been unshipped, unfortunately. But I'm still going to show you my demo because I was really happy when I made it. So, sorry. All right, and what shared array buffers are, it's a mutable shared memory, which is pretty scary when you think about it. Say that to any programmer, and they get this glazed look in their face. I'm like, don't do that. I did it. OK. So what does this look like when you could use it? Well, you would create a shared array buffer. You would post message it into your worker. But instead of post messaging the entire thing and creating a copy or transferring it, it creates a link, which means that you mutate it in one spot, it gets updated in the other spot because it's shared memory. So in this example, I'm passing in a shared array buffer and then counting to 10,000. Again, not super realistic, but if you need to count to 10,000, this code will do it for you. Yeah, shared array buffer. Good, great. OK, so I added a bunch more zeros onto that, and then this is what we got. So what the code is doing here, let me explain this, is when I click go, post message is messaging into my worker and saying increment by 1. The worker is then messaging out and saying, hey, here's my new result. And it does that up to a very large number. Shared array buffer does the same thing. But because I don't have to post message out every single time, and because it can just read from that shared array buffer value, I get to work around that 14 or that 10 milliseconds of latency for every call, which means that the shared array buffer is super fast for doing this, where the post message approach is maybe not super fast. So a little bit more context, because this is a little misleading. This is with a 6x slowdown, and again, it's at least 7 or 8 additional zeros on the end of that I don't show. OK, great. So maybe I have you sold on workers, and you think they're awesome and super fast, and you can make really awesome Bitcoin mining apps with, but they seem a little hard to use, and I agree. But luckily, there are some cool higher-level abstractions that you can use today. Some frameworks already ship with some basic support for using workers. Preact, there's a demo here where you can drop Preact's DOM diffing algorithm directly into a worker, and it works great. Angular actually works with workers by default, and you can flip a flag and build your application to run in a worker, which is kind of amazing because you don't have to change anything for the most part. There's a cool library from Surma from the Chrome team called Comlink that makes a very easy-to-use message bus in between a worker and your main thread, where you can pass messages and you don't really have to think about it. It's very easy to use. You can expose objects much like you can export from a module. So the right side is your worker code, and your left side is your main thread. And then finally, Workerize, which is a library from Jason Miller. He just came out with this, and it allows you to automatically offload modules into web workers on the fly. What does this look like? Well, it looks like this. You basically pass a stringified version of your code into Workerize, and then you can call functions on it. And he made a nice abstraction on top of this called Workerize Loader, so you can drop it into your Webpack config and get these wins right away, hypothetically. So, OK, cool stuff, interesting, but where do you go now? What do you do? Well, I'd recommend that you experiment. Try out some of these APIs, see what works, see what doesn't, make some demos, see if you can break things, and provide some feedback. If you tweet at Chromium Dev, this will get to someone who cares, and they will reply. So thank you very much. It was a pleasure.